All right, so welcome to Math 310, Introduction to Modern Algebra. And so we are on lecture 13 today. And so what I want to do is mostly talk about applications of the material we've done, as well as some material you should hopefully have seen in previous classes, might have seen but not really processed, why it was important that you saw it. And then if time permits, but probably won't, talk a little bit more about rings. So there's a lot of things that you have done over the years in your math classes where they haven't maybe emphasized as much as possible why you should care. I have a lecture on logarithms that I sometimes give because most people are introduced to logarithms as statistic teachers want to introduce more functions for us to work with and have no justification at all as to why we should care. Can anybody give me one or two reasons why we should care about logarithms other than teachers care? I know some of you are going to be teachers, and so you want to be able to explain to your students, why are you learning this? I'm sorry? In what way? Good. So if you take the log of relationships, often things that are not linear become linear. We are very good at understanding straight lines. So one of the great powers of logarithms is it takes nonlinear relationships and can make them linear under a change of variables. The other is it allows you to talk about things of many orders of magnitude apart on the same scale. You can talk about a proton and a galaxy and have them on the same way. So there's a lot of things that you've seen that you maybe haven't really been told why you care about that. And since a lot of you are going to be going out on the front lines as teachers, I thought this would be a good class to do. So again, if you haven't handed in your homework and exams, please do so. If you've emailed them to me, that's fine. Okay. So on the first class, we talked about RSA, which is one of the best ways to encrypt information. One of the reasons it's so great is we believe it's secure, at least with current technology, and it can be done very rapidly. And so it's not enough to be able to do things. We need to be able to do things quickly. Is it hard in some sense to factor a number? If I give you a number, is it hard to factor in principle? If you had all the time in the universe, could you factor a number? Yes. Would you enjoy it? No. Right? How would you factor the number?
Go through each possibility.
Go through each possibility, right? And it would take so long that it would not be practical. So what's wonderful about the method over here is not only does it works quickly. Now, unfortunately, there are always advances in technology. And what is secure at one point may not be secure in a few years. And so if any of you have been following quantum computing will be able to handle stuff like this. And so people have already shifted to other methods of encryption. So just to quickly summarize what goes on, we choose two secret prime numbers, P and Q. They should have at least 200 digits. I'm keeping the numbers small just so that they display nicely on the screen. And we choose some number D, and we make public the product P times Q, and some special number E. So D is going to stand for decrypt, E is going to stand for encrypt. And D and E have this remarkable property that when you multiply them, you get a remainder of 1 when you divide by P minus 1, Q minus 1. And if you want to send a message, you can send any message of a number that's at most n. You raise it to the eth power, and then to decrypt, you just take what you receive and you raise that to the dth power. So we've talked about why this works and why a lot of the concepts we've been learning in group theory come into play for stuff like this. I want to talk today a little bit about the issues with execution. So there's four main issues. The first is, how do we find large primes and what's large enough? So that I have a reasonable sense of security. The next is, how do we find E and D so that E times D is 1 mod P minus 1 Q minus 1? The next is, how do we compute M to the E mod n efficiently? And the last is, can an eavesdropper determine D from E and N? And when I say determine, I mean determine efficiently. I don't care if the universe dies a heat to death, and billions, trillions of years later, Eve says, I've got it. Can Eve get it in the next century? I'm doing a mathematical biology project with a couple of colleagues, and one of my colleagues is a little bit concerned because the model is unstable in the limit of infinite time. I'm really not worried about predicting alligator populations in Florida, a billion years from now. If the model is even accurate after 5 years, I'm surprised because so many things are going to be changing. I'm not worried about long-term effects like this. So the last one, can Eve determine? We don't know. It is possible that somebody has a way to do this and they haven't made it public yet. I don't know why it doesn't. Oh, there you go. Now I was in the mountain. So this is still unknown. If you can figure out how to do this efficiently, do not publish. Talk to me privately. Okay. I do some work in. I will stop here. I will not say anything further while the camera is recording. If there's time at the end of the class, I might say something else. But I know too many people who've said things with. So if you can figure out how to do something like this, there's a lot of really good movies that warn you as to what will happen if you make that knowledge public. All right. The next is, how do we compute m to the e mod n efficiently? We already did that. That was fast exponentiation. And we talked about how multiplying in general is expensive. If I want to evaluate a polynomial of degree d, it was of order d squared calculations, but then we used Horner's algorithm to reduce it from order d squared to order d. That's great, but if d is of size 10 to the 200, that's still, a universe of universes of supercomputers running since the dawn of time. If that's not enough computational power to solve the problem, we're dead. But when we used fast exponentiation, we saw that instead of taking d steps to multiply, it only took log d steps. Log d we could do. The log of 10 to the 200, that's less than 1,000. That's not so bad. So we're left with two real problems. How do we find the e and the d, and how do we find large primes? So does anybody have any thoughts about what we might have seen that might be useful in finding e and d so that e times d is 1 mod p minus 1 q minus 1? Anything you've seen very recently? Thought? Euclidean algorithm, right? So do we remember what p minus 1 q minus 1 is? There was a special name for that number when p and q are 2 primes. You've seen that expression before. Anybody remember where we've seen that? So this was the same as phi of pq. The number of numbers relatively prime to pq. It was the number of elements in the multiplicative clock group. And so imagine d and phi of pq are relatively prime. Then there was a suggestion, let's use the Euclidean algorithm. So by the Euclidean algorithm, there exists A and B such that AD plus B phi of PQ equals 1. Thus, AD is congruent to 1 mod phi of PQ. So what should we take E to be? So what would our E equal? It would just be so we're trying to find a number such that when we multiply d by it, we get 1 mod phi of pq. So we found numbers a and b such that ad plus b phi of pq was 1. So what should we take e to be? We've got it from the previous line. What do we have here? We have a times d is 1 mod phi of pq. So what should we take for e? What do we multiply D by and get 1 mod phi PQ?
A.
It's just A. So we take E equals A, we win. Have we found a way to always find E? Is this always going to work? Are there any assumptions? Yes. Yeah, we start off by saying that they're relatively prime. So if they're not relatively prime, this is not going to work. So now the question is, how likely is it that D shares a common factor with phi of PQ? If D shares a common factor with phi of PQ, what could you do? So we have to find some D with some E such that E times D equals 1 mod P minus 1 Q minus 1. I'm not wedded to this initial D that I chose. So if my initial D doesn't work, what do? Choose a different one. And what if that doesn't work? Again, and if that doesn't work? Again. So if not relatively prime, if GCD of D and phi of PQ is greater than 1, choose a new D. Keep going till get a GCD of 1. So what's the next question we want to ask? So what would you ask now?
What do you do once you get it?
Well, no, once we get it, then we're fine. Then we can find our E. And this step here is fast. This is fast by the Euclidean algorithm. But we need a D that's relatively prime T. So we keep going until we get. So we're concerned about efficiency. What's the concern we might have? How long it takes. So I'll make this extra credit. Prove doesn't take too long. I have to resist the fact that this is not a number theory class. So I'm not going to prove right now that you can do this without too much trouble. And by not too long, I mean on the size of the log of the number or the log squared of the number, something like that. Anything, a power of logarithm is not going to be a long time. You could try to find primes where P minus 1, Q minus 1 doesn't have that many prime factors. If you were able to do that, then you might be able to find a D much easier. So for example, if P minus 1, Q minus 1 has a lot of prime factors, it's easier for the GCD to be greater than 1. So wouldn't it be nice if P minus 1 and Q minus 1 were prime? How likely do you think it is for P minus 1 and Q minus 1 to be primes when P and Q are large prime numbers? So how likely do you think it is that P minus 1, so best case, P minus 1, Q minus 1 are prime, and P and Q are big primes. Big takes up less space than large. How likely do you think it is for a large prime number that P minus 1 is prime?
0.
0. Why is it 0?
Prime number minus 1 is going to be an even number.
It's going to be even, right? So absolutely no chance of the best case happening. So you know it has to be a multiple of 2. What's the next best case? So best reasonable hope. We know P minus 1 can't be prime because it's a multiple of 2. what's the next best hope? So you know p minus 1 is a multiple of 2. What would be the best thing that could happen given that it's a multiple of 2? What would you hope is true about p minus 1 over 2? That would be prime. And what would you hope about q minus 1 over 2? That would be prime. Is that possible? Can somebody give me a prime that's big, at least 5, such that p minus 1 over 2 is prime? 7. So if p equals 7, then p minus 1 over 2 is 3. If p equals 11, then you get 11 minus 1 over 2 is 5. So it's always true, right? We have 2 data points. I see one person shaking their head in disgust and another person giving me a fake thumbs up. So how would you disprove this conjecture? Yeah, give me a counterexample. Almost any prime you choose is going to work. Yes. 13. So if p equals 13, then that would give us 13 minus 1 over 2. That's 6, so it's false. So these are very famous primes, the Sophie-Germain primes. It is believed that there are infinitely many, and they actually have an interesting role in proving Fermat's last theorem. If your exponent x to the n plus y to the n equals e to the n, if your exponent is a Sophie-Germain prime, there's actually an elementary proof. We have wonderful heuristics for how many such primes there should be up to a given height, completely unknown. So what I like about this part over here is just when you're going into the classroom, some of you, to teach, try to get your students to conjecture. Try to have them gather some data and see, hey, does this conjecture work? The first couple of ones I chose, it's always working. 7 worked, 11 worked. And how'd you come up with 13? Oh, who gave up? How'd you come up with 13?
I knew that it was 12.
But why did you choose 13?
I don't know. I saw it in the future.
Okay. I was wondering if you chose 13 because it was the very next prime. Here we had done 7, we had done 11. Sometimes small data can be misleading. Okay, so the first question, we've kind of glossed over this. Are there infinitely many primes? If there are only finitely many primes, then there's just a list of things that people can try. If it's a large list, we might still be okay. There are 10 to the 500 primes. That's such a large number, we're going to be fine. How many of you have seen Euclid's proof of the infinitude of primes? Okay, so only 3 people, though I know at least one other person in the room has seen the proof. Hopefully. So this is a really important question to ask. We want to study primes, we want to use primes. How many do we have to play with? Are there infinitely often? Do they happen infinitely often? So the first proof goes all the way back to Euclid. Copyright has clearly expired. Assume only finitely many. So we can list them all, P1, P2, P3, all the way up to Pn. And we can consider P1 times P2 ... times Pn plus 1. There are 2 possibilities. Let's call this X. X is prime. Case 2, X is not prime. If X is prime, could that list have been complete? No. We listed all the primes. X is clearly larger than all the primes. As X is greater than P1, P2, ... Pn, it is a new prime, not on the list. Contradiction. Okay. So case 1 can't happen. What about case 2? Imagine x is not a prime number. X is greater than 1 and it's not prime. So what must be true if I give you a number that's greater than 1 and it's not prime? It's composite. So x greater than 1, not prime, therefore it's composite. So there exists a p dividing x. And I claim p does not equal p1, p2, or any of the primes. As what happens if I divide x by p1? What's the remainder? So what's the remainder if I divide x by p1? So it's x is the product of p1, p2, p3, pn, and then I add 1. So what would be the remainder if I divide x by p1? Yes. Well, no. So for example, let's say x equals 2 times 3 times 5 plus 1, which would be 31. What would be the remainder of 31 when I divide by 2? 1. What would be the remainder of 31 when I divide by 3? What's the remainder of 31 when I divide by 5? 1. If you look at it, x is a multiple of p1 plus 1. So when I divide by p1, its remainder is? It's also a multiple of p2 plus 1. So what's its remainder when I divide by p2? 1. So all the remainders are 1. Thus, we found a new prime. So this is amazing. We have just shown that there are infinitely many primes. Now, the next question you can ask is how many? I'll leave this as an exercise. Implies the number of primes at most x is at least a constant times the log base 2 of the log base 2 of x. The truth is about x over the natural log of x. Very far from the truth. So in some sense, while 0% of numbers are prime, a good number of numbers are prime. How many numbers are there less than or equal to x such that n is a perfect square? Approximately how many such numbers are there? So about how many numbers less than x are a perfect square? So if x was 100, how many numbers less than 100 would be a perfect square? What would be the perfect squares less than 100? 1. What's next? 4, 9, 16, 25, 36, 49, 64, 81, and then 100. So we go all the way up to 10 squared. So how many numbers less than 100, less than or equal to 100 are a perfect square? 10. If I went up to 400, what's the largest number whose square is less than or equal to 400? 20. If I went up to 900, how many would there be? 30. If I go up to x, how many numbers approximately would have a square at most x? You might be off by 1, but you'd be pretty close. When it was 100, we had 10 numbers. When it was 400, we had 20 numbers. When it was 900, we had 30 numbers. Square root. So that's about square root of x. How many n are there less than or equal to x such that n is a perfect cube? It would be approximately cube root. So there's a lot more primes than perfect squares or perfect cubes. You could even add up all the perfect powers. You could say, how many numbers are there n less than equal to x such that n equals m to the k for some k greater than or equal to 2. And that's going to be roughly of size square root of x. That's a nice exercise. And the idea going on here is when x is large, the number of cubes, perfect cubes, is much less than the number of perfect squares. So the fact that you have square root numbers that are perfect squares dwarfs the extra gain you get from the cube roots, dwarfs from the fourth roots, dwarfs from the fifth roots, and so on and so on. As a nice exercise, try to make this rigorous. Try to show that the higher, it doesn't really mean that almost all of the numbers are going to be governed by this. So this tells us that there's at least infinitely many primes. So if we want to do something like RSA, we at least have infinitely many primes to look at. The growth rate we get is absolutely terrible. I will add with just one more, oops, shoot. I had copy, not paste, so. So we had the process, x was p1, p2, ... pn plus 1. Let's see what we get. When n equals 1, we have the prime 2. So x is going to be 2 plus 1, and that gives us what prime? 3. So now when n equals 2, we have the primes 2 and 3. So x equals 2 times 3 plus 1, which is 7, which is also prime. When n equals 3, we have the primes 2, 3, 7. So x is 2 times 3 times 7 plus 1, which is
43.
43. What's true about 43?
Prime.
Prime. So what question should you ask? It's okay if it's wrong. Based on this data, with 3 points of data, what would you ask? Is it always prime? What do you think? What should we do? Either prove it or Google it.
Find a counterexample.
Find a counterexample. So we could try to do the next one. Do you have access to, say, Wolfram Alpha to just plug this in? Yeah. So given that we have somebody with access to, so we take n equals 4, we have 2, 3, 7, and 43. So x is going to be 2 times 3 times 7 times 43 plus 1. So that's going to be 42 times 43 plus 1. How many people think it's going to be prime? How many people think it's not going to be prime? What do you get? Oh, it's taking time to load. 7. It's 42 times 43 plus 1.
It's 1807.
1807, and it's 1807 prime. So prime Q 1807. It's not a multiple of 2, it's not a multiple of 3, it's not a multiple of 5. It's both. Is this composite?
Yeah.
So it's composite. So the conjecture died very quickly. I'm sorry? Multiple of 13. But this is what you want to get into the habit of, is you want to try to make conjectures, you want to get some data, and then refine your conjectures.
Maybe the conjecture problem take the first n primes and multiply them, like 2, 3, 5 of them.
Could be. And so that's a salvage. So salvage is maybe if we let xn be p1, p2, ... pn plus 1, that's prime. So work for 2, work for 3. So then if we tried x3, that would be 2 times 3 times 5 plus 1, which is 31, which is prime. If we did x4, that'd be 2 times 3 times 5 times 7 plus 1. So that would be 30 times 7 is 210 to 11, which is prime.
So it will fill for up to 13. You go up to 13, all of a sudden it's 1.
So then it eventually fails. Okay. So what that means is we need to do even more to fix it. So is there any way to make a fixable statement from this? So the first attempt failed. The modification failed. Is there something you can do? Is there a string maybe? Maybe you don't take adjacent primes. Maybe you do every other prime. Is there something you can do where it will always be prime? In mathematics, whenever possible, it's nice to have more than one way to prove something. So another thing we can look at is from our primes or from our numbers. So we define the from our numbers by the following. Fn is 2 to the 2 to the n plus 1. Are these prime? Always? If not, how often? It should look a little bit strange as to why am I looking at 2 raised to an even power? And not just an even power, a power of 2. Consider x to the n, let's do it as 2n plus 1 equals 0. Can somebody give me a root of this equation? So can you give me a number that satisfies this equation, x to the 2n plus 1 equals 0? -1. So we know x equals -1 works. So we can now factor this, and you all remember your long division from. So this factors as x plus 1, and then with a little bit of work, you'll get x to the 2n minus x to the 2n minus 1 minus x to the 2n minus 2 minus ... minus x plus 1. Okay. So if x equals 2, then 2 to the 2n plus 1 is never prime. Because we just showed if I take x equals 2, I can write this as 3 times something. Okay. So the only chance I have, to be prime is exponent is a power of 2. And that's why we look at Fn is 2 to the 2 to the n plus 1. Those are the only ones that have a chance of being prime. Okay. Keep doing copy rather than paste. So let's calculate a couple of values. Fn is 2 to the 2 to the n plus 1. When n equals 0, what's f0? That's going to be 2 to the 1 plus 1. That's going to be 3. Right? When n equals 1, f1 is going to be 2 to the 2 to the 1. That's 2 squared plus 1 is 5. When n equals 2, we get 2 to the 4th plus 1, 16 plus 1 is 17. When n equals 3, it's getting a little bit harder now. We get 2 to the 8th, that's 256, plus 1 is 257. And when n equals 4, we get 2 to the 16. It's like 65, 536. So it's
I get 65,537.
5,000. That's right. That's what I thought. I thought it was 65,536, and then you add 1.
Yeah.
And anybody know what's true about all these numbers?
First three are fine.
They're all prime. All of them are prime. So it was a big question, are these numbers always prime? When you take n equals 5, it's composite. It took people a while to find that out, but it is composite. We believe these are the only ones that are prime. It's very hard to hit the prime numbers. These sequences growing so rapidly. If people are interested, again, I'm happy to just throw out some topics that if you want to hear more about, happy to meet individually. There are great heuristic arguments that show that there should only be about 3 times in the sequence. And yeah, 3 to 5, 3 to 4, it's about the right number. So we don't believe anything else in the sequence is prime. Here's a great way to prove that there are infinitely many primes by looking at the Fermat numbers. It turns out they satisfy this relation. Fm plus 1 is F0 times F1 ... times Fm plus 2. Okay? How would you prove this? Any thoughts on how you might prove this? One way is to try to prove it by induction. How else? The one is induction. There's another way. Brute force. Use, Fn is 2 to the 2 to the n plus 1. Maybe somehow you can make it work. So it's a nice exercise to prove this relation. And if you can do this, the GCD of Fm plus 1 and Fk equals what? For k less than or equal to m. What can you tell me about the GCD of Fm plus 1 and Fk? So this is very similar to what we saw with the Euclid argument. When you use something more than once, it's a technique. What happens when I divide this by Fk? What's the remainder? I'm sorry? 2. So what's the only possibility for the GCDs? What are the only possibilities? So can Fm plus 1 have any common factors with Fk? Can something divide both Fk and Fm plus 1? What do you think? What's the remainder when you divide Fm plus 1 by Fk? 2. If the GCD was 5, if 5 divided Fm plus 1 and 5 divided Fk, then 5 would have to divide the remainder of Fm plus 1 when we divide by Fk. So what are the only possibilities for the GCD? 1 and 2. So the GCD is 1 or 2. But, Fn is always odd. So what's the GCD? It's 1. So we've just proven that these numbers are relatively prime. So exercise as relatively prime, each number gives a new prime not previously seen. So when I look at F1, F1 was a prime number, F2 is a prime, F3 is a prime, F4 is a prime. If F5 is not prime, it has to be divisible by a factor that's not included in F1, F2, F3, F4. And I got a new prime not on my list. When I look at F6, I get a new prime not on my list. So this is just a good way to review a lot of the things we've been seeing in the class. Looking at the remainders and getting some consequences from this. We have now shown that there must be infinitely many primes. So it's a nice exercise, put in the details. So if you want to have practice writing up proofs, not under exam conditions, this is why I'm giving you so many things like this. If you want some extra practice of writing something up and getting some feedback, here's something to do. Write this up rigorously. Write this up rigorously. Here is another way to prove it. As a mathematician, you either work on a napkin if you're lucky enough to have a napkin near you, if not, whatever piece of paper you have. And so what I did is I said, well, what if I take my numbers and I multiply by high powers of 2 and subtract? Then this is very similar to the Euclidean algorithm, that when I subtract multiples of that, it shouldn't change the GCD. And can I keep walking down? And so this is a sketch that I did of you're just trying to do it in the beginning, enough to convince myself that yes, this would work, and this would show that the GCD is going to be 1. So try to make this rigorous. This was enough to convince myself that if I subtract the appropriate powers of 2, if I do this enough times, I will eventually get the GCD is either 1 or 2, and I know it can't be 2, because they're all odd numbers. Okay, just as an aside, how many of you have seen the Riemann zeta function? Okay, so there are certain things which you should at least see once before you leave your undergraduate career if you're going to call yourself a math major. Just so that if somebody comes up to you, you can pass some initial tests. And so the Riemann zeta function is defined to be the sum, n goes from 1 to infinity, of 1 over n to the s, where the real part of s is greater than 1. This is one of the most important functions in all of mathematics. So does anybody know what year this is? This is the who's awake right now. It is what year? Yes? 2025. Okay, so you're now in the hot seat. What number follows 2025? What's the next integer?
6.
And after that? And after that? So we actually have a formula for the nth integer. Do you know what the formula is for the nth integer? F of n equals n. We actually have a formula for the spacings between adjacent integers. Do you know how long you have to wait for the next integer? 1 unit, right? The integers are well understood. It turns out that this equals the product over p prime, 1 minus 1 over p to the s inverse. It's nice to prove this. It uses the geometric series formula plus the fundamental theorem of arithmetic. And this is called the Euler product, after the famous mathematician Euler. Does anybody know if 2025 is prime or not? Clearly not prime, it's a multiple of 5. It's also a multiple of 3. 2026 is not going to be prime. 2027? Maybe. If you're taking an exam like the Putnam, you need to know what is the next prime from whatever year you're at. That's a good thing to know, is the year you're studying prime. This is good to know for math competitions. If I give you a prime number, is it easy to find the next prime? No. It was not that hard to ask you what's the next integer after 2025, after 2026, after 2027. We have very nice formulas for that. We don't have nice formulas for what is the next prime. Yes.
So it's really not bad at finding prime numbers.
Yes. Yes.
We figure out a way to find like where prime numbers may be more frequent, or are they distributed in any like sensible pattern?
So depending on the scale you're looking at, yes and no. When you really zoom in, strange things can happen. When you zoom out far enough, a lot of things balance out. And so on, far enough scale, there's a tremendous amount of structure. But when you start to zoom in, things become very random. There's what's called prime races. Are there more prime? So if you throw away the prime 2, every other prime is odd. And it's going to have either a remainder of 1 or a remainder of 3 when you divide by 4. And the question is, which one happens more often? And it was discovered that it seems like you always have more primes 3 mod 4 than 1 mod 4. And it was eventually proven that they flip infinitely often, but almost all of the time there's more primes 3 mod 4. And so there's a lot of really good questions related to this that you can ask, where we can answer the questions under certain assumptions that we think are true, but cannot prove. And so these questions about the fine structures of primes are extremely challenging. On short scales, it's hard to say anything. On big scales, things average out and we can say a lot. So over here, the point I wanted to make today is one of the key things in mathematics is to convert what you want to understand to something that you can understand and somehow pass the information back and forth. Most of you are not going to become professional group theorists. Most of you are not going to become professional mathematicians using stuff like this. That's fine. But I want you to get this idea of, I try to construct something that connects what I know to what I want to study. We know the integers. We don't know the primes. And the hope is that we can pass from knowledge over the integers to knowledge over the primes. So for example, zeta of s is the sum, n goes from 1 to infinity of 1 over n to the s. It's the product over p prime, 1 minus 1 over p to the s inverse, the real part of s greater than 1. If we take the limit as s goes to 1 from above of zeta of s, that's going to be the sum of 1 over n. This is the harmonic sum. What does that equal? Who remembers this from calculus? 1 plus a half plus a third plus a fourth. Exponential would be like with like factorials, and that would give you e. So anybody remember the harmonic sum? So today is the day to just go over things that you might have missed from previous classes.
Not just E, is it?
Nope. If you had factorials, it would be e. Does this sum converge or diverge? Yes, it diverges. All right, so this sum diverges. Therefore, must be infinitely many primes, as otherwise the product converges. All right. Given that people don't seem to remember that it diverges, let's quickly show that it diverges. So the harmonic series diverges. There's a couple of proofs. Let's do a non-calculus. We have 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth plus a ninth all the way up to a 16th plus dot dot dot. So this is proof by grouping. One third and 1/4. You agree that each of these is at least 1/4. So this sum is going to be greater than or equal to 2 times 1/4. 1/5, 1/6, 1/7, 1/8. They're all greater than or equal to 1/8. So this is going to be greater than or equal to 4 times 1/8. For the next one, it's going to be greater than or equal to 8 times 1/16. So the sum is going to be greater than or equal to 1 plus a half, plus a half, plus a half, plus a half, and so on and so on and so on. So this is one way to show that it diverges. Another way to show it diverges is you could write the harmonic sum as the evens plus the odds, right? Which do you think is larger? So let's do this on a new page. So H will be the sum of 1 over n. H even will be the sum of 1 over n and is even. And H odd will be the sum of 1 over n and is odd. Assume the sum converges. So H equals H even plus H odd. Which do you think is larger, the sum over the odds or the sum over the evens? So the odds is going to be 1 plus a third plus a fifth plus dot dot dot. The evens is going to be 1/2 plus a fourth plus a sixth. Which do you think is going to be larger?
The odds.
The odds, right? So H odd would be greater than H even. I claim H even equals 1/2 H. Because H even is 1 over 2 times 1 plus 1 over 2 times 2 plus 1 over 2 times 3 plus 1 over 2 times 4 plus dot dot dot. So I can just pull out a 1/2 from everything. So if that's the case, I would get H equals 1/2 H plus H odd. Therefore, 1/2 H equals H odd, or H equals H odd plus H odd, which is greater than H odd plus what did we just show H odd is greater than?
No, H even.
H even. And what's H odd plus H even? H. So we just showed that H is greater than H. So if you assume that the sum converges, we just showed a contradiction. And then I'll do one last proof of this important result, the integral test. And this actually gives you an idea of how quickly it grows. 1 plus 1/2 plus 1/3 plus 1 over n is approximately the integral from 1 to n of 1 over t dt. Do you remember the integral test from calculus? The way to calculate sums is to convert sums to integrals. Does this look familiar to anybody? And so you need to figure out what function has derivative 1 over t. So what function has derivative 1 over t? Natural log. So this is going to be, the natural log of n minus the natural log of 1, which is the natural log of n. So not only does the sum diverge, but we actually have an idea of how rapidly it diverges. So, this is just a good way to review some of the stuff you've hopefully seen. Right. The last thing is, I sadly will not be teaching you in March, so I will show you something of a specific day in March. Anybody know which holiday mathematicians celebrate in March? Pi Day. And for the people who don't like Pi Day, there's a holiday that people celebrate in June. Does anybody know the June holiday? Anybody know? It's June 28th. Anybody know why people would celebrate June 28th? Yes, 2 times pi. It's tau day. So the question is, which is the better constant, pi or tau? If you look at the area of a circle, it's pi. If you look at the perimeter, it's 2 pi. So depending on what you're looking at, sometimes one constant is better than another. There's some great YouTube videos on this. Zeta of 2 is the sum of n goes from 1 to infinity of 1 over n squared is the product over primes of 1 minus 1 over p squared inverse. It turns out this is known to equal pi squared over 6. This implies that there are infinitely many primes because we know pi squared is irrational. If only finitely many primes, then the product over p of 1 minus 1 over p squared inverse would be rational. Therefore, pi squared would be rational. Contradiction. So this is a really nice special value proof that there must be infinitely many primes. And this was considered a different type of proof because it gives you no idea of how rapidly the primes are growing. And so just to make you feel better, whenever you make a mistake, this is the worst result I ever proved in my life. The final version, which was published, was a little bit better, but we initially showed, or I initially showed before I bought McDonald's, I showed that the number of primes less than or equal to x is at least log x. So a couple of things to note. Euclid gives, log x. The truth is x over log x. So I am far from the truth. I'm much worse than Euclid. And I'm doing this by doing a very involved proof using properties of the Riemann zeta function, expanding this out, talking about how well can you approximate irrational numbers by rational numbers. And by doing all of this work, I get the result of log x. And my proof used a rationality measure, bounds on pi squared, which used the prime number theorem, that the number of primes less than or equal to x is about x over log x. So by assuming that the number of primes up to x is about x over log x, I was able to show that there's at least log x primes. I dare you to have a worse mistake in your career than that.
Well,
They published the final version. So the reason is I was doing theorem shopping. I was looking up to see what results do we know about how irrational pi squared is, and I saw a certain result, and I just used it without reading the paper. And when I finished the argument, I got this really crappy result. I'd use stronger language, but this is being recorded, and I don't want to, content violation slashed on this. I got log, which is terrible. And then I went back and I looked at the paper, and the paper needed to calculate a bound for the least common multiple of the numbers from 1 to x. I said, well, the least common multiple is clearly going to be at least as large as the product of all primes up to x. And then it used the prime number theorem to say how many primes there were, and imagine they were all the smallest numbers. And so this is a great warning that whenever you're using a result, you have to be careful and check what are the conditions being assumed. Sometimes people are not good about stating what conditions they're assuming. When I was a postdoc somewhere, like a proud parent showing the newborn baby, one of the grad students who worked in the same area as I did came up to me and said, here's my theorem, here's my thesis. I thought you might like it because we work in the same area. And I looked at it, he goes, very nice. And I flipped through it, he goes, by the way, do you know that half your thesis is wrong? And his heart just stops. I knew he was using, from just skimming the introduction, he was using a specific paper which said, we assume k is congruent to 0 mod 4. If k is congruent to 2 mod 4, the argument follows similarly. All you have to do is add a minus sign for the other half cases and his thesis is fixed. It was a very trivial fix. But it really drove home the lesson to him about how careful you have to be. I don't like papers that don't restate the conditions with the theorem. Sometimes the paper says, for this whole paper, we're going to assume the following. And then in the theorem later on, they don't reiterate the condition. Somebody had a proof of the Riemann hypothesis that I was refereeing a while ago, and the expert referee could not find a mistake. And so I'm now going through it line by line, and I finally find, oh, he took this theorem from a chapter of a book, and in that chapter of that book, they assumed the Riemann hypothesis in that chapter. They don't restate it again when they wrote the theorem. And so I am saying this as a warning to you that whenever you're using things, make sure you satisfy all the conditions. My result wasn't wrong, but just kind of useless. If I assume that there's x over log x primes at most x, I can prove there's at least log x primes. Yeah, I can prove that by just saying log x is smaller than x over log x, done. By working things out, we actually ended up getting a nice result. So the final paper does have some good results, but the whole point of this was just as a warning. To just finish our discussion of primes, so this was going back to what we were doing before, of multiplying the numbers in Euclid and taking the first prime number that divides them. So it goes 2, 3, 7, 43, 13. The next one is the next number, the smallest prime that divides it is 53, then 5, then huge number, 139. Another small number, 11, 17, moderate number. And this is an extremely hard sequence to understand. What are some questions you might ask about this? So we're taking the Euclid method, we're multiplying all the primes on our list and adding 1. If it's prime, we add it to our list. If it's not prime, we add the first prime that doesn't divide it. What's a good question to ask? So you want to be able to come up with questions. Doesn't matter if it's a good question right now. What's a question you might ask? We're trying to understand the primes. We take this Euclid method, we multiply all the primes on our list, we add 1. And if the number is prime, we put it on the list as the next entry. If not, we put the smallest number, the smallest prime that divides that on the list. What might you ask about this list?
Is it infinite?
Is it infinite? And the answer is yes, because we know every time we do Euclid's argument, it's either going to be a new prime or it's going to be divisible by prime not on a list. So good. So we know the list is infinite. What else might you ask about this list? Yes. Does it eventually contain all the primes? No idea. Completely open problem. And now let's assume I'm divinely inspired and I am told that it does. What's your next question once you know that it contains all the primes? So I look at it, I see 2, 3, I see 5, I see 11. So 7, 11, 13, 17. Does anybody see 19? I don't see 19. Does anybody? Oh, I see 19. I see 19. Okay. 23. I don't see 23. Second line. Okay, somebody sees 23. All right. 29. I see 29. End of the second line. 31. Unless I read 13 backwards, I don't see 31. So another natural question you could ask is, how far do I have to go to see a prime? Do I have to look at maybe p elements on the list to see the prime p, or p squared elements, or maybe e to the p elements? If every prime occurs on the list, how long do you have to wait? You want to get in the habit of asking good questions. And then if you keep asking good questions, eventually one of them is going to work out for you in life. It might be for the specific problem you're looking at, the question is too hard. But get in the habit of looking at data, asking questions, and then trying to investigate. All right, so how do we find large primes? How large is large? We've actually talked a little bit about using Fermat's little theorem. So using Fermat's little theorem. And that said, if P is prime, and the GCD of A and P and P equals 1, then A to the P minus 1 is congruent to 1 mod P. And if you remembered that, that made one of the homework problems this week much easier, because you could then reduce a lot of calculations, and you can see that the two polynomials were the same. This is really, more generally, if the GCD of A and N equals 1, then A to the phi of N is congruent to 1 mod N. So if GCD of A and N equals 1, and A to the N minus 1 is not congruent to 1 mod N is not prime. So this becomes a way to tell that certain numbers are not prime. So we use this to find a proof that 6 is composite, right? We proved 6 was composite. Yep. 5 to the 6 minus 1. 5 squared mod 6 was 1. So this was the same as 5. So this was the same as 5, which is not equal to 1 mod 6. So 6 is composite. So this test allows us to quickly determine that certain numbers are not prime. Unfortunately, it doesn't give us a conclusive test that something is prime. Just because you pass a lot of tests doesn't mean that you are prime. You might begin to gain some confidence. If I pass 1,000 tests, if I choose 1,000 different values of A, and for all of them it works, I'm feeling a little bit better. People remember Pythagorean triples? We've seen them before because we had Pythagorean square day. So I could give you, A, B, C with A squared plus B squared equals C squared. There are infinitely many. 3, 4, 5, 6, 8, 10, 12, 15, 20, 15, 20, 25. I can generate many. Are you impressed about the infinitely many that I'm generating? No, because they're really all the same number. They're really all the same triple. I'm just changing my scale. This is why it's much better to study A over C, B over C with A over C squared plus B over C squared equals 1. Because then all of those triples would collapse to being the same. So over here, when I'm trying 1,000 different A's, maybe I think I'm trying 1,000 different A's, but maybe they're really all the same A in a way that I don't know. So I might not be gaining additional evidence. I may not be making things stronger. It might just look stronger. I think we did this. We did the 100 Caesar ciphers, right? I think at the start of the semester, that if I encrypt something with 100 Caesar ciphers, so let's say FC of X is X plus C mod 26. I could apply 100 Caesar ciphers, C1 of X. I need more space. And then I could apply another Caesar cipher to that. And then I could apply another Caesar cipher to that and do this 100 times. And when you think about how many possibilities do I have, I've got 26 to the 100. And you can say, well, but one of those is doing nothing. So, okay, fine, 25 to the 100. 25 to the 100 is huge. When you think about how many possibilities this is tremendous. You're not going to guess with a 1 out of 25 to the 100 chance of success. But we said that this is the same as what? I apply 100 different Caesar ciphers. How many possibilities are there if I apply 100 different Caesar ciphers? At the end of the day,
25,
20, oh, no,
26.
26, right? I could end up, applying maybe add 5, subtract 5, add 4, subtract 4. At the end of the day, this is just f of C1 plus C100 mod 26 on X. So even though I thought I was building incredible security by doing 100 Caesar ciphers, no, it wasn't that much more secure. So be very careful. So even if I pass 1,000 tests, unless you can convince me that those tests are independent, it may not be extra information, it may not be extra security. So again, a lot of today is just giving you some warning for when you leave college and you go out into the real world. Be very careful if somebody is showing you information. They may be showing you some information in a very special way to get you to believe what they want you to believe. Any fans of the movie My Cousin Vinny? Classic Joe Pesci, Marissa Tomei comedy. Talks a lot about how if you show people information in certain ways, you can mislead them. It actually came up in one of the impeachment hearings where they were not allowing people to hear the discussion. They could only read the transcript. And when you are reading the transcript, you miss the tone of voice. That something might have been said sarcastically. That something might have been said as a question, not as a statement. So be very careful with how people present information. So it turns out that unfortunately, there are numbers that pass the Fermat's-Little theorem test for any choice of A and are composite. So just because you always pass does not mean that you're prime. So I went to Wikipedia, source of all knowledge, fountain of all wisdom, and just, pasted a few things here. So if you want to read, either go directly to Wikipedia or look at the notes. But unfortunately, these numbers exist. And then the next question asked is, how many of these numbers are there? How frequent are they? Are there enough to worry about them? What kind of properties do they have? And there's lots of things you can ask. It was shown that there are infinitely many Carmichael numbers. I'm glad that one of my friends and colleagues, Thomas Wright, who went to a high school that was rivals to mine in football, he actually proved that there are infinitely many arithmetic progressions. And a lot of the stuff we were doing in groups actually is very useful for tackling questions about progressions. We know there are infinitely many primes. Are there infinitely many primes congruent to 1 mod 4, congruent to 4 mod 4? One of those questions should be very easy to answer. Do you think there are infinitely many primes congruent to 4 mod 4? Or 0 mod 4? What would it mean for a number to be congruent to 0 mod 4? What kind of number would it have to be?
Have to be a multiple of 4.
Have to be multiple of 4. Do you think there can be infinitely many primes that are multiples of 4? No. So the big result is, if I give you 2 numbers that are relatively prime, there are always infinitely many numbers congruent to A mod B, as long as A and B are relatively prime. And the key idea in that is using the groups we've been studying. These clock groups come into play for stuff like this. You know enough to read one of the most influential papers in the past, I'd say 2 decades. It's not really done in practice, but it's nice to know that it exists. We have ways to determine if a number is prime, but we don't necessarily know that these methods will work and will run. They will if certain well-believed conjectures hold. And if those conjectures are true, then the methods we have will work. But it's possible that those conjectures are false, and then when we try to do this, it will eventually not run in a reasonable amount of time. So as a big question, is there a deterministic way to tell if a number is prime? And can you do that quickly? And the measure of quickly is some power of the log of the number. Why the log of the number? That tells you the number of digits. So if I give you a number that's 100 digits, the log of that number is going to be around 100. And the only methods we had for the longest time were either probabilistic or they worked assuming certain well-believed conjectures held. An computer scientist in India and his 2 undergraduates found an algorithm that worked around on 2002. And the algorithm is very simple. It's just put over here. The first thing you do is you check to see if your number n is the power of an integer. It's not that bad to check to see if your number is the power of an integer. You can do this in log time. Take the square root, take the cube root, take the fourth root, any of those integers. Do you need to take the fourth root? No, if the square root doesn't work, the fourth root won't work. So you can check very easily to see, is your number a power of an integer? The next is you find the smallest r such that OR of n, the order of n, is greater than log squared of n. So the paper talks about how you do this in a reasonable amount of time. And then if it turns out that a certain GCD is between 1 and n, that means I found some number a that has a common factor with n. The number must be composite, right? If the GCD of n with a is greater than 1, n can't be a prime number. And what this is telling us is we only have to check a up to this number r, which isn't too big. And then we basically do something. We look at x plus a to the n, and is that congruent to x to the n plus a mod x to the r minus 1 and n? I don't want to go into the details. I just want to do enough to show you that the stuff that we're doing on rings actually has applications. It's looking at these rings and doing the algebra in these rings that allow them to determine a really good deterministic primality test. If you want, the paper's not that bad to read. I had mentioned theorem shopping earlier. To some extent, that's what they were doing in some places. They were theorem shopping with number theorems and say, hey, do you have any theorems that would tell us that we will find a prime if we go this far, if we look this far? Nope, 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 yes. Oh, good, okay, yes, good, we'll use that one. And so they were very careful to make sure which theorems they used, that all the conditions were met. And so again, this is just a nice way to see that what we're doing has applications, because we need a quick way to tell if a number is prime. In practice, you don't really use this. You use the algorithms that are conditional on certain algorithms, certain conjectures being true. Run the algorithm. If it works, great. If it doesn't work, then you can resort to this. We believe those conjectures are true. We've never had the algorithms not work in practice. But if that ever did, we have something that we can fall back on, and it's nice to know we have this. So I'm going to give you something to think about for next time. So this is one of my favorite riddles. Consider an army with 10 generals, or if you want, you can consider something even more powerful than an army, an academic institution. Okay? And you want a security system such that any 3 of them can launch the nuclear missiles, but no 2 of them can. I'm just a visiting professor. I don't know about Siena's nuclear arsenal capabilities. I don't know if you're allowed to say anything, but no, I can't say anything in public. Okay. Okay. So I mean, at Williams, I do know that if Amherst, acts up, we can deal with Amherst. Any 3 Williams professors, but no 2 Williams professors suffice. So the question is it possible to devise a system using a polynomial such as ax squared plus bx plus c, quadratic polynomial, to launch the missiles? You must input the coefficients of the polynomial, a, b, c. So you have to give information to the generals so that any 3 of them can figure out A, B, and C, but no 2 of them can. So you're to think about over fall break is there a way to do this? Now, instead of having any 3 of them being able to do it, I could have any 4 or any 5 or any 6. And that would just change. If I wanted any 4 of them, I would now have a cubic, because a cubic has 4 coefficients. If I wanted 10 of them, I would have a polynomial with degree 9. You can also play some games. You could say certain people are more important than others. Who is the most important person at an institution like this?
Head of the board of trustees.
Head of the board of trustees. Excellent. Right? Not the president, head of the board of trustees. So the head of the board of trustees should have enough information that if they want, they can launch. And maybe the president can launch so long as 1 dean or 3 faculty members approve. So the question is, you can actually devise a system like this to give different people different amounts of power. You could also take into account that certain people may not be independent. I have a family member who did not believe that they and their spouse could use the high-speed carpool lane because they were married and they legally count as one person. Okay, so no, just because you're married does not mean, in fact, we encourage you because you're almost surely leaving from the same destination. Use the carpool lane. But maybe when you're trying to decide who gets what information, maybe if you have two people who are married, maybe they should not be two of the three people to launch. And so there are lots of nice ways you can tweak stuff like this. So this is something to think about. And what I like is, if you're teaching, younger kids, they've seen polynomials, and a lot of times in school, here's the quadratic formula, find the roots, do it 40 times, and people might get good at using the quadratic formula, and they'll get even better at hating mathematics. Here's a way to use the quadratic formula in an interesting manner. We can use this to set up a system of security. And the question is, how do you give information? And so think about what information you want to give people so that no two people can launch, but any three people can launch. And then just as a final aside, a lot of what we were doing when we looked at rings involved irrationality. We saw that if things were quadratic irrational, things were nice. If things were cubic irrational, we had to have more terms. We couldn't just do a plus b alpha. We had to do a plus b alpha plus c alpha squared. And so natural question is, when can you determine if something is irrational or not? So irrational means it's not a ratio of two integers. So here are two papers I've written with students. Hopefully everybody has seen the standard proof that the square root of 2 is irrational. This is almost a requirement to be a math major. Assume the square root of 2 equals a over b. Without loss of generality, we can assume a and b are relatively prime. If not, remove all common factors. So we then square things and we get 2b squared equals a squared. So 2 divides a squared. So a must be even, because if a was odd, and this is actually a little bit of work. So if a equals 2k plus 1, then a squared would be 2k plus 1 times 2k plus 1 would be 4k squared plus 4k plus 1, which would be 2 times 2k squared plus 2k plus 1, which is odd. So there's a little bit of work here. What we really want to do is we want to use if a prime divides a product, then it has to divide one of the two factors. We saw some issues with that with some of the rings. This is a non-trivial thing to prove. And if you looked at the ancient Greek arguments, I think they only went up to the square root of 17 was irrational, because proving this in general is a little bit hard. As a nice exercise, prove the square root of p is irrational, or if n is not a perfect square, prove the square root of n is irrational using an argument like this. But this gives us that a is even, so we can write a as 2m. So 2b squared is 4m squared, so b squared is 2m squared. So the same argument now gives us 2 divides b. Well, if a and b are relatively prime and 2 divides a and 2 divides b, that's a contradiction. Therefore, the square root of 2 is irrational. So everybody has seen this proof. So at Williams, all students are required in the math department to give a public talk before they graduate. Is there anybody here who is planning on a career in mime? If so, I'm not going to make you say anything, but just raise your hand. Okay, so nobody's planning on being a professional mime. So you're all going to have to speak. So we require all of our students to give a public talk in math before we let them graduate. And so somebody was giving a talk years ago on multiple proofs of the square root of 2 being irrational, and they gave this beautiful geometric proof. And this goes back to Tenenbaum. And what they did is they said, assume that the square root of 2 is not irrational. So I assume I can write it as a over b. I take a square of side length a. I take 2 squares of side length b. This region inside is double counted. These two regions are not counted. So this area that's double counted equals the sum of the two whites. And you end up getting a smaller situation and you get a contradiction. So if anybody's interested, the papers are online. I'm happy to chat with you. I was sitting next to Professor Morgan, who remarked, it's a shame it only works for the square root of 2. And of course, like all of you, whenever somebody is speaking, you give your undivided full attention to the speaker. A split second after the talk ended, I slipped a napkin to my colleague with the proof for the square root of 3 using equilateral triangles. It's amazing how quickly you can write in a fraction of a second. And then the question is, how far can you push this? You can get square root of 5 using pentagons. If somebody can get square root of 7 using geometry, I will give you an A+ in this course. There's a lot of counting to do with pentagons. I'm not going to go into that. This is just so that the slides have been shown. So if you pause the YouTube video, it is there. To get the square root of 6 was a little bit more involved, but we were able to do that. I'm not going to go through all the details. We're able to extend this argument by looking at these equilateral triangles, and we can get numbers of the form square root of n plus 1 over 2. Does anybody recognize what these numbers are? The first few are 1, 3, 6, 10, 15. Anybody know what type of numbers these are?
Summation of the integers.
Summation of integers. These are the triangle numbers. And this is a great place to end. So we could show the square root of 3 is irrational. The square root of 6 is irrational. The square root of 10 is irrational. The square root of 15 is irrational. Do you think we can show the square root of every triangle number is irrational? What comes after 15? After 21? 28? After 28? Argument. So you just added 7, so now you have to add 8. Do you think we're going to be able to show the square root of 36 is irrational? What's great is when we were doing this proof, we knew it was going to have to break down. That there was going to be an obstruction that would have to emerge, that it would not be allowed to push this forward. So again, a big question in some of the things we're doing is, we want an irrational number. How do we find these irrational numbers? Are they actually there? We needed these for constructing some of the rings. Some of the applications for these rings are in, cryptography, encryption. So the stuff that we're doing has real applications. For the next class on content, which is going to be on Tuesday, is think about the general code. And I want to hear when class starts, anybody's suggestions on how to do this. All right, I am going to hit stop now.